there's several types of orbital changes that affect the climate. They're all long term, and they're called the Milankovitch cycles. One of them is the change in the tilt of Earth's axis, which varies over a 41,000 year period between 22 and 24.5 degrees. And then there's also the precession of Earth's axis, which acts like a top. So right now, Earth's axis is pointed at the North Star Polaris, and in 10,000 years, it's going to point the other way towards Vega, in which time we're going to have summer in December and winter in July.
Today on the podcast, I am excited to have Dr. John Bird, an atmospheric scientist and engineer at the world's largest operating nuclear power plant. With a PhD in experimental science, space science, and extensive time spent in both the Arctic and Antarctica, Dr. Bird has a profound understanding of Earth's extremities. A former lecturer at the Imperial College London, he has authored numerous peer-reviewed papers. John, it's good to have you today.
Right. Thanks for the introduction, and thanks for having me on your show. It's fun to be your first guest, so that's great.
Yes, awesome, John. Without any delay, let's jump into the questions. I know you're an atmospheric scientist, spent many years in the industry, so I'll start off with the very basic question out there. I know in today's day and age, climate change is a big concern for everyone. We're talking about the transition to net zero, going off the fossil fuels. So if you could quickly explain in simple words what is net zero transition and why do we care about it?
Sure. Net zero is the balance between residual carbon emissions and carbon removal. And by residual, I mean the carbon emissions that are left over after we've removed most of the emission sources. So that's going to leave some residual emissions like from aircraft and possibly cement production or steel production. And it's those residual emissions that potentially could be removed from the atmosphere by the so-called negative emissions. And at that point, the temperature will stabilize. But it doesn't tell you anything about what the temperature is actually going to be when it stabilizes, because that depends on the amount of CO2 at the time, which isn't going to be anytime soon because we don't yet have the technology available at scale. So that's something we can discuss. But in any case, as we head down in the emissions towards net zero, it doesn't mean the temperature is going to go down, because not until we actually stop emissions will the temperature eventually stop going down. And even then, even if we stopped emissions today, there's a lot of thermal inertia in the oceans that's going to be released as the temperature gradually comes down. So we're looking at a minimum of several hundred years before it gets down to the pre-industrial levels. And another problem is that when we do eliminate the carbon emissions, we're also eliminating the associated aerosols. And the aerosols act as a cooling agent because they reflect sunlight. And so that's another example of upsetting the balance between the incoming and outgoing energy balance. So once we remove the aerosols, we've removed a cooling effect. So we've got an additional warming immediately incurred. So stopping the carbon emissions isn't going to bring down the temperature right away.
Okay. Uh, to follow up on what you just said, you mentioned there's a lot of latent thermal energy in the water bodies across the globe. If that is the case, would it be fair to say that no matter what we do by we as humans. The effects of climate change are not something we as humans can control, or do you think it's the acceleration in the degradation of our climate that is something we can prevent by taking proper steps by decarbonizing our supply chain?
If we do decarbonize and achieve net zero, then the temperature will stabilize and eventually it will start coming down as the carbon dioxide gets absorbed by the oceans and the ground. But that process is hundreds of years.
Right. Okay. UN mentioned we have targets to achieve 1.5 degrees Celsius before 2050 as compared to the pre-industrial era. How achievable do you think those targets are? And why is the number 1.5 degrees Celsius important? Why not 2 degrees? Why not 1 degree Celsius? What's so important about this 1.5 degree number?
Well, the 1.5 degree number isn't some kind of a sudden tipping point or anything. It was just made as a arbitrary target, but there's no way to achieve that now because we're all almost there right now. We're just months away actually from going over 1.5. If you look at let's say a moving average of 1 year, but right now we're also having the effects of El Nino, which is providing a bit of extra heat. Although it's not a source of heat per se, it's an oscillation between the oceans and the atmosphere that happens over a period of a few years. But in addition to that, we have aerosols, and there's been a reduction in the aerosols in the last few years, which is causing some possibly acceleration of the global warming. Because in 2015, there was a bunch of regulations put in place to reduce the sulfates coming from ships. And then they were further enhanced in 2020. So as a result, the aerosols have been reduced, which is good because they're a major problem for human health. But in cleaning up the atmosphere that way, it's caused uh, a reduction in their cooling effect. So that's been bringing some extra warming. So once you subtract those effects, we're still trending upwards. Like there's been no decrease at all in the rate of increase in the CO2 going into the atmosphere, as uh, as can be seen by what's called the Keeling curve that shows the CO2 that's been going up since, well, it's been measured in a high resolution since the 1950s, but it's been going up ever since the mid 1800s.
Okay, because you mentioned the Keeling curve and the CO2 going up since the late 1800s, what argument would you present to someone who says no matter what us humans we do in terms of burning fossil fuel, using carbon-based energy sources, climate change is something that will happen regardless? How do we rationalize the human impact on the global climate? And what could be said about us accelerating this problem?
Okay, well, first of all, starting with how we know that the CO2 is causing the increase in temperature, we can look at the correlations that we've seen between carbon dioxide and temperature over both the long term and the short term. And there's always been climate change and there's been cycles. And it goes back, let's say we can measure it going back 800,000 years at least, when we've got detailed measurements of the temperature and CO2, which have been measured in the ice cores of Antarctica. But we know that there's been climate change uh, going back to the beginning of the Earth because of the orbital cycles and other natural forcings that affect the balance of the energy coming and going from the Earth. So, for example, volcanoes and changes in the solar irradiance are both natural forcings that affect the balance of the energy. And anytime you change the balance between incoming and outgoing energy, it's going to change the temperature. And the
Right.
orbital changes, there's several types of orbital changes that affect the climate. They're all long term, and they're called the Milankovitch cycles. One of them is the change in the tilt of Earth's axis, which varies over a 41,000 year period between 22 and 24 and a half degrees. And then there's also the precession of Earth's axis, which acts like a top. So right now, Earth's axis is pointed at the North Star Polaris, and in 10,000 years, it's going to point the other way towards Vega, in which time we're going to have summer in December and winter in July. So those are examples of the long-term cycles.
Right.
And what is there's another important cycle is in the eccentricity of Earth's orbit. It varies between circular and more elliptical, and that one has a 100,000 year period, and that one is important for climate change. But those are just the natural forcings. We've also got the anthropogenic forcings on top of that, which are the CO2 providing warming and the aerosols providing cooling. And in addition to these forcings, there are feedbacks, which are mechanisms that can amplify or diminish an initial warming. So the main ones are water vapor and the polar ice cap. So in the case of water vapor, as the temperature goes up, the water vapor evaporates more in accordance with the Clausius-Clapeyron relation, which states that for each degree in temperature warming, you get 7% more capacity of the atmosphere to hold moisture. And it's the water vapor is actually the most important greenhouse gas. And so the evaporation causes more heating, which causes more evaporation, more heating. It's a feedback cycle. And then the other positive feedback cycle is with the polar ice caps because as they melt, it exposes more of the darker ocean, which absorbs more heat. And also, you're reducing the amount of reflected energy. So, again, the net effect is an increasing in temperature. And these are balanced by negative feedbacks. The main one is that as the Earth heats up, it radiates more energy out. And so the question is, what's the combination of all these effects, the feedbacks and the forcings? How can we determine the net result? And for that, we can use climate models, or we can look to the past to see what's actually happened. And for that, we have a handy time machine in the Antarctica ice cores, where we can look at samples of the ice under the surface of Antarctica, which is up to 3 kilometers thick. And it's like tree rings because each year another layer of snow piles on top of the previous layer, pushes it down and compresses it, and it traps the air. And by digging it up, we can measure the carbon dioxide concentration for that year and also the temperature for that year. And the result, going back for the last 800,000 years, was a cycle in the temperature and the CO2, both well correlated with a 100,000 year period corresponding to the Milankovitch eccentricity cycle. And the CO2 during this last 800,000 years varied from 2 to 300 parts per million. But ever since the mid 1800s, when the steam engine was invented by James Watt, the temperature and CO2 have both shot up. Again, well correlated on both long term and short term. So that gives a clue as to what's causing the temperature to increase. But there's further evidence in the ratios of the isotopes. Because if you look at the ratio of carbon 13 to carbon 12, you can see that it's gone down while the CO2 has shot up over the last 150 years. And that's because the carbon being emitted is carbon 12 because it's coming from plants that prefer carbon 12. And then when they were buried millions of years ago, they took the carbon 12 with them. And then when we burn them now, we see the carbon 12 returning. So we know it's not caused by volcanoes, for example. And then the
Right.
other evidence is that we know that CO2 absorbs infrared light. Um, the spectrums are well known, and we know that carbon dioxide is expected to absorb infrared light. And so it comes as no surprise that it does block the outgoing infrared, acting like a blanket. So anyway, all this establishes the anthropogenic origin of the climate change in the last 150 years.
Right. Okay. So to summarize what you just said, we have natural cycles that switch after every 10,000 years, 100,000 years, depending on what cycle we're talking about. But one of the biggest evidence we have is the evidence of carbon 12 that's available in today's day and age, because that's what we use as fossil fuel. And the increase in carbon 12 is what's accelerating the the climate change problems we're seeing, and we can verify that using the 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 graphs, the charts you mentioned, and we can see a trend in an increased rate of change of climate as compared to what it used to be maybe 200, maybe 300 years ago. So
That's
does
right.
that, yeah,
That's an excellent summary. Yeah. So the base temperatures didn't really take off until mid 1800s, but then we didn't really have high resolution measurements until 1957 when David Keeling, a scientist, was trying to measure the CO2 with this newfangled high resolution spectrometer. And he found that the CO2 varied a lot from day to day and place to place. So he really wanted to find a pristine environment where the air was well mixed and it was away from any sources of pollution. And so, because it was 1957, it was the same year as this big international scientific campaign called the International Geophysical Year. And there were a lot of funding available for science experiments. So he was able to set up observatories on Mauna Loa in Hawaii and at the South Pole. So he started measuring the CO2 at 315 parts per million, and he found that in the summer the level went down about 5%, but then in the winter it came back up again. And he found that in each year the peak was a little bit higher than the previous peak. And the same measurements have been going on every day at the same two observatories up till now. And it's been one of the longest and most famous measurements in scientific history. So after the baseline of 300 parts per million, it's gone up to now 440 or so. There's been almost 50% increase since the pre-industrial times.
Okay, that makes sense. I know you talked a lot about measurements. I know you have spent a significant amount of time in the poles of the Earth. You've spent time in North Pole, also spent time in Antarctica. Could you talk a little bit more about your experience there, how life was living there, and how long did you live there, and the types of measurements you took?
Yeah, well, my work in the Arctic was at an observatory called Astrolab up on Ellesmere Island, about 9 degrees of latitude from the North Pole. And this observatory was set up to measure the processes in the upper atmosphere using LIDAR and other optical instruments. So, one of the instruments we used was interferometers to measure the winds and temperatures of the aurora. And we also used LIDAR to measure the meteor trails, which leave layers of sodium and iron. And we could also look at polar mesospheric clouds. These are really brilliant blue clouds that you can see um, in the summer if you're at a high enough latitude. Although you don't want to be too high because it has to be night. You need the sun about 6 degrees below the horizon to see them. But with LIDAR, we can see them anyway. And we had a similar experiment set up at the South Pole Station in Antarctica. And one of the processes we were looking at was these so-called gravity waves, which are actually buoyancy waves that take energy from the lower atmosphere, and it's like breaking waves on an ocean. They deposit their energy up in the upper atmosphere, and it can influence the chemistry and winds. And we also looked at these polar stratospheric clouds down in the lower stratosphere that provide some of the chemistry for ozone depletion. And we looked at the ozone hole and how the ozone moves around. And we also use the LIDAR instruments to study the aerosols, which, as we discussed, are important for the energy balance of the Earth, but they're also one of the most sources of uncertainty in the climate models. So it's really important to establish the influence of the aerosols on the energy budget.
Right. Okay, that's interesting. Like, I think you spent over a year in Antarctica. That is one experience not many people have. It's amazing to know how we do all these types of measurements that eventually gets used by governments, agencies across the globe to make decisions on what the best thing is in terms of the energy transition. How do we need to find new sources of energies?
No, I was just going to say that on the topic of new energy sources, I know that you've looked into this. Perhaps you could kind of give us an overview of just what are the main demands for energy in the Earth in general, and how much of it's really being provided by fossil fuels.
Sure, John. You know, as you probably already know, that like today's day and age, most of our energy comes from fossil fuel sources, coal being one of them. United States has started to phase out its coal use. Canada has already started to do that as well. Ontario, provinces, Canada, doesn't use any coal, and the last coal power plant was shut down back in the early 2010s. Um, but then again, we have parts of the globe like China, India, who rely on coal as their primary source of energy. But that's about to change. Globally, we are seeing um, a public uh, a public decision to move away from fossil fuels, find alternate sources of energy. Some of the more popular ones are hydroelectricity, power from dams, nuclear. We both have been working in the industry for quite some time, so nuclear is definitely one of the best available baseload energy sources out there.
So,
And by
which
baseload,
of
I
these
mean,
sources do you see as the most promising for combating climate change?
John, I think we need to look at baseload energy. Baseload energy is something not many people talk about. It's the energy acquired from source that is enough to sustain a grid. If we think of the grid as a big system, a system that constantly needs a certain level of energy, certain level of power, then to sustain that big system, we need a baseload source.
So,
Something
for grid,
that's
you're talking about the distribution network of the electricity,
That's
correct?
correct. That's correct. That's correct. Um, Sources like nuclear, coal, which can be 24/7 all throughout the day without interruption. Those are the types of energy sources we need to look at. I mean, although we have solar and wind, but these are very intermittent sources, which means we might have the solar energy powering us for 6 hours during the day when the sun is up, but when the sun goes down, we have no energy. Same goes for wind. We might have a lot of wind energy for a few hours during the day, but if the wind goes away, then there's no energy.
What about the
Sorry,
potential
John,
for
go ahead.
us? What about storing the energy?
Right.
Do you
I think that's a great point. Storing energy on a large scale, on a grid scale, would enable us to store the energy from solar, from wind, from all these other intermittent sources during the times we have the ability to store them, and then we could dispatch them when we need them.
okay? So, can you give us an idea about the potential for the small nuclear reactors?
Sure, John. To begin with, small nuclear reactor or small modular reactor are called as SMRs. It's a very popular technology in the government space. Utility companies really like it. Basically, small modular reactors are nuclear reactors that use uranium and they use fission to produce energy, but only upwards 300 megawatts. The distinguishing factor about these reactors are that they're very compact, they're small, as the name suggests, and it's ideal for isolated remote locations. As of now, we don't have a lot of small modular reactors built on this planet, but more and more companies and utility companies, government agencies are working together to create more and more of these small modular reactors.
So, the idea would be to set one up in some northern community where they're currently depending on diesel power. Is that the idea?
But yes, one of the use cases is having these SMRs in very isolated locations where you generally don't have a grid reaching all the way to power the city. Uh, it's a fantastic use case to replace the diesel power generators.
They can also apparently be used for applications other than directly supplying electricity, like for example, heat, or how does that work?
Yes. So the idea behind SMRs is to produce energy, and these are best suited for industries which are hard to abate. For example, producing energy from coal, and this is used in many industries, like steel smelting uses a lot of coal to produce the heat that's required to make steel, to melt the metals. SMRs is an ideal source of energy for these types of hard to abate industries. It can also be used to power homes, like small localities houses up to a few thousand residential units, office spaces, office parks. All of these could be powered by SMRs if they could be deployed uh, in a very safe, reliable, and a cost-effective manner.
And what makes them cheaper, like on a per capita basis?
Right. John, as of now, we don't really have a very cheap, ready to use SMR yet. Most of the SMRs are still in the development phase, which means they're still working out the way to design these reactors, the best way to deploy them. So we don't have that cheap factor with us as of now. But the idea is once you can, you know, you can say this proof of concept reactor works, and then you start scaling this reactor technology and start deploying it in multiple locations. Then, once the economy of scale kicks in, we would then have a lot cheaper electricity from these SMRs as compared to the traditional conventional big reactors. Similar to producing vehicles for. The more you make, the more profit you make based on economies of scale.
Right. So, what are the prospects for building an SMR in Canada?
Right. Based on what I've read in publicly released information, news releases, I think the utility companies in Ontario, they are looking into different technologies uh, to make and deploy an SMR. I know Hitachi, GE, these are one of the companies that are involved in this process. They will be one of the first ones to make a small modular reactor. And if Ontario does it before anyone else, I believe it will be the first one in North America to produce a small modular reactor. I know in the United States, they're also working to create these types of small modular reactors. Westinghouse, that's one company that's involved in the design phase of it. And I know companies in France, they're involved in these types of projects. EDF, utility company that operates most of their large nuclear reactors, they're looking into different options to make small modular reactors. The Russians, they're trying to make one, Rosatom, that's the Russian state utility company. They're looking into different technologies for SMRs. And also the Chinese. They have been working on this for quite some years now. And all these companies, not just the big nations, even smaller countries like Romania, uh, I know countries in Africa, they're also looking into the prospect of SMRs. So there's a bright future ahead for these types of reactors.
Okay, great. So, are there any other technologies other than the solar and SMRs that you see as a great potential for replacing some of the fossil-based sources?
No, John, that's a very good question. We do have, if you think about it, we only have a few sources of energy on this planet. It's either fossil based or it's stuff we can get from the environment, wind, solar energy, or using water, tidal energy, or the potential energy of water in hydro dams to basically produce energy. But one energy source which is very new is a concentrated solar power. The idea is very similar to using solar energy to basically make energy. Basically, concentrated solar power is the use of sunlight focused on mirrors that are positioned in such a way that the rays of sun are concentrated at a single point, creating high amounts of heat energy. It's then this heat energy that's used for secondary purposes. It can be used to heat water, which can be used to spin a turbine, produce energy that way, or it can also be used to directly supply hot water as a heating fuel to houses. So that's one technology that I think is still in the early stages, but in the next few years, we could definitely see more of these deployments, especially in areas that receive a lot of sunlight. I know there's one in Morocco. There are deployments in India that are looking into these types of technologies. So that's something the high sunlight countries could always look into.
Right. So it sounds like we have a lot of upcoming technologies that are going to help us on the quest for net zero.
Yes, yes, I feel like it won't be one silver bullet to solve this problem. I think it's going to be a mix of different energy sources, mix of different energy systems that eventually will all work in synergy to fight climate change, get human dependence off of fossil fuels, transition to something that's much cleaner and much more sustainable in the long run. So I think it's all of these things combined that will help us out. What do you think about that, John?
Yeah, I agree. We're a species that's good at solving problems, and we've always come out in the past for whatever solutions we've needed, but it's nonetheless a challenge because the technology is yet to be developed and there's not much time, so we're going to really have to depend on these technologies that you've outlined.
Right, right. That's true. Well, John, it was a fantastic conversation I had with you today. Thank you for coming on the show as my first guest, and look forward to many more of such conversations in the near future.
Okay, well, thanks a lot for having me on your show, and it's been an excellent summary of where we stand and the potential for a lot of development in the future, and we've given the challenge, so we'll see what happens.